Hello, yes. Hello, friends. Good evening to all. Myself, Akshay Kumar, YA Chair, ASHRAE Chandigarh chapter. So, welcome to this webinar jointly organized by ASHRAE Chandigarh chapter and ASHRAE Falcon chapter. And this is also supported by the youth at ASHRAE. I am sure you all are aware about ASHRAE. ASHRAE is the American Society of Heating, Refrigerating, and Air Conditioning Engineers. This society has mission to serve humanity by advancing art and science of HVAC and R and their allied fields. This society consists all the professional members related to HVAC and building industry. With the initiation taken by ASHRAE Chandigarh chapter to spread knowledge among the members during the lockdown period. So today is our 70th webinar on fundamentals of UVGI for air and surface disinfection. To go through with the activities done by ASHRAE Chandigarh chapter or any other region chapter. If you are ASHRAE member, then it's very good. If you are not, then be a part of ASHRAE by register yourself online at joint.ashrae.org. Now, moving to the ASHRAE Code of Ethics. In this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core value of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall avoid all real or perceived conflict of interest. Now, I would like to introduce today's presenter, the chair of ASHRAE Epidemic Task Force, Mr. William P. Panfleth. He is PhD, PE, Fellow ASHRAE, Fellow ASME, FISISQ. He is a professor of architectural engineering, the Pennsylvania State University, USA. Presidential member, he's a presidential member of ASHRAE. He's a ASHRAE distinguished lecturer. He's a chair of ASHRAE Epidemic Task Force. So now recording of the webinar will be uploaded on YouTube channel. Please subscribe our YouTube digital channel ASHRAE Chandigarh. Question and answer will be done at the end of session. You can ask your question by typing in chat box and same will be answered at the end by speaker. Now I request Mr. William P. Panfleth, please present your presentation. Now over to you, William sir.
Yes, thank you. I'm waiting. How do I share my screen? There we go. Are you seeing my slides or are you seeing my email?
Yes, sir. Yes, sir. Please share your presentation.
What are you seeing at this point? Is it? Are you? I clicked share.
No, sir. We are not seeing your presentation. Please share your presentation, please.
I've clicked show screen. Which screen are you seeing?
Sir, we are seeing ASHRAE. We are seeing your email now.
Yeah. Okay. So I'm
now our PPT is.
I know what I need to do. Hang on. I need to do this.
We again your email is.
Is that better? I switched screens.
Yes. Yes. Now this is visible, sir.
Okay. Then we're good to go. Thank you very much for inviting me to speak today. This is my first visit, in quotes, to the Chandigarh chapter. I hope to be there in person someday. And greetings also to UAE Falcon chapter. I have been there a couple of times during my my travels. And I see there are almost 500 people on the webinar this morning. I'm very glad to be with all of you. this evening where you are, perhaps, and the morning where I am. The talk today is very relevant to the current situation. I've been studying ultraviolet disinfection for more than 20 years, but there's never been more interest in it than there is today, and that's very appropriate because, as you'll see, it's a technology that can be very effective for controlling infectious diseases. So I'll be giving you an overview of many aspects of that technology today, and hopefully, if you're interested in applying it, this will get you started. I'll give some references at the end that you can read further. So this is an ASHRAE Distinguished Lecture presentation, so it's been registered for various professional development credits. We'll go past that right to the outline. So these are the topics that we'll cover this morning. Introduction through fundamentals, through applications of UV system types, some discussion of its effectiveness as shown in the literature, a little bit of economic analysis, and a case study of a modeling analysis, and then conclude. Hopefully that will not take an hour. So to the introduction, a few words about different microorganisms and control alternatives to UV, and a bit about the history. So what we're talking about here is controlling any type of microorganism, bacteria, virus, or even fungi in some cases, but we're very concerned about bacteria that cause serious diseases like tuberculosis and anthrax and MRSA, multiple drug-resistant Staphylococcus aureus, viruses that cause various illnesses from the cold to SARS, influenza, and today COVID-19. These come from infected humans, and in some cases they may be biological terror agents. Back in the early 21st century, we had a number of incidents where anthrax was sent around to buildings as a biological terror agent. So the characteristics of these microorganisms is that they're very small, from microns to nanometers in size, but they typically ride on particles, droplet residues that are produced when someone coughs or sneezes, and also possibly on dust particles that they get attached to. The transmission modes that are common for these diseases that we can do something about are airborne transmission and fomite transmission. Airborne transmission means transmission through the air that is inhaled, could be at relatively short distance, could be at longer distance. Fomite transfer is transfer involving an intermediate surface. So infectious material goes from an infected host to a surface such as a countertop or a doorknob or even someone's hand, and then is transferred to someone who's susceptible. So with this technology, we can address both of those. Fungi are the other type of microorganism that we may be able to do something about. These generally don't cause infectious diseases, but they're implicated in many other problems such as allergies and asthma attacks. They can be opportunistic infections that afflict people who are immune suppressed. If they've had an operation, have been given immunosuppressants, say for a transplant operation, or if they have a disease like AIDS that will suppress the immune system. So these grow in the presence of food and water. They're not coming from an infected host typically, and those include things like Aspergillus, Stachybotrys, and Penicillium that we find in buildings that have moisture problems. So these grow on surfaces. They create mats or mycelia, and spores of fungi are generally much larger than bacteria or viruses. They can be in the 1 to 10 micron range. They produce some VOCs that can be irritants, and they also produce substances called mycotoxins that are also air contaminants if they become vaporized. In HVAC systems, we find these growing on cooling coils and also on damp filter media and other surfaces. So how can we control these various microorganisms? For pathogens, one of the best methods, as we have been hearing about regularly in guidance on suppressing the COVID-19 pandemic, is to limit person-to-person transmission with good hygiene. So this means hand washing, it may mean distancing, as we've been doing, or even sheltering in place, lockdowns that were mentioned in the introduction today. For fungi, the best thing to do to control fungi is to control the source by keeping buildings properly dehumidified and preventing moisture intrusion by the way the envelope of the building is designed. So those are really effective ways to control many of these microorganisms. For all of them, if we can't do those things, we have a certain number of engineering controls that we can apply to inactivate or kill them in occupied spaces or in our systems. So we can use particulate filtration to remove particles that contain microorganisms from the air. We can dilute air with ventilation. We can, on surfaces, do chemical surface cleaning, and in the air and on surfaces, we can inactivate using various technologies. So filters are quite effective if we get filters that will handle the right particle size. All of these biological agents that can be airborne are filterable to some extent. Even individual viruses, although they generally don't exist in nature because they're shed in respiratory droplets that have proteins and salts and other things in them that will not completely evaporate. So a respiratory droplet will evaporate to a particle that's substantially smaller, but not as small as a virus. So the effectiveness of removal with a filter depends on the particle size and the efficiency of the filter. There's a chart over on the right-hand side of this figure that shows typical grade efficiency curves, efficiency of removal versus particle size for filters that are rated according to the ASHRAE standard 52.2 MERV rating system, minimum efficiency reporting value. That rates efficiency in 3 different size ranges down to 0.3 micrometers. And the larger the number, the better the filter. So you see at the bottom there, MERV 6 and MERV 8. Those are the filter sizes that are currently the minimum requirements in ASHRAE's ventilation standards. MERV 6 for residential buildings in 62.2 and MERV 8 and for non-residential, non-healthcare facilities in 62.1. Now those filters are not very effective for small particles that may contain microorganisms. What we really need is a filter that is going to be effective across the, say, 5 micrometer and smaller range. And that takes at least a MERV 13 filter. If you look at MERV 13, the most penetrating particle size around 0.2 micrometers for this representative curve is about 40%. Even better than that, though, and still relatively in the same price range and performance characteristics is MERV 14, which could be 60% and higher in that range. So these are filters that now ASHRAE in its COVID-19 guidance is recommending that building owners and operators upgrade to if they have filters that are more of the efficiency range that are associated with our minimum ventilation standards. The really high efficiency filters, HEPA, for example, that's 99.97% efficient for particles of 0.3 micrometers in the test procedure that's used to rate them, are expensive and have high pressure drops, and they're not a very feasible retrofit in many systems, although we can use portable air cleaners that have HEPA filters in them. Filters remove particles, but the media, if it becomes wet, can actually become a place where fungi and bacteria will grow, and you can see a contaminated filter over there on the left-hand side in this figure. viruses don't generally multiply outside of a host. So when viral particles get into the air, they may be collected by a filter, and as long as they remain active, they may contaminate it. But we don't have a high level of concern that if a particle has been on a filter for several days, that it poses a large risk of infecting someone. But at the same time, we recommend that filters be handled carefully if they're being changed during the pandemic. That those who work with them should wear personal protective equipment, gloves, masks, and bag the filter and clean up carefully after they're done working on it. So filtration works, but to do it properly may require more cost than we're used to investing in filters in buildings. Ventilation, of course, will dilute all contaminants that are airborne, but depending on the climate in which a building is located, this can be a very expensive energy proposition. Hot, humid climates in particular, where many of the people on this call are probably living. So it also has its good points and its less good points. UVGI is an example of a technology that inactivates. We won't talk about the others here, but there are several that don't actually remove particles from the air or remove them from the building by displacement. It uses mainly ultraviolet C and ultraviolet B radiation from the 200 to 320 nanometer spectral range, as shown on the image here. And that damages the DNA and the RNA of viruses, bacteria, and fungi. There are base pairs in DNA, for example, adenine and thymine base pairs that connect together, and the photons of light in this range will break the bond, and the thymine bases will form dimers, and that damage is what contributes to the inactivation of the microorganism, so it can't repeat itself. We'll look at that in a little more detail in a bit. Susceptibility of microorganisms to UVC and UVB varies greatly. The main wavelength we use, for reasons I'll explain, is about 254 nanometer UVC. I have an example here on the screen with anthrax and with the bacterium that causes pneumonia. And we see there that when we irradiate them with the same strength of 254 nanometer UVC, that the strep is reduced almost to nothing over a period of 2 seconds with 500 microwatts per square centimeter, while anthrax hardly responds at all. So it's important to know what you're trying to disinfect and to design the system properly for it. For some resistant microorganisms like anthrax, filtration may be a better option. Anthrax is a fairly large spore and fairly easily filtered with sub-HEPA filtration. And we can also combine UV and filtration to get an overall high system inactivation and removal efficiency as well. So now fundamentals about how microbes respond and UV sources, and a little history as well. I want to emphasize to everyone that this is not a technology that just emerged in the last few years. The study of disinfection with light actually goes back to some fundamental studies in the 19th century, and there were applications of UV for water treatment prior to 1910. There was an actual working water treatment plant that began operation around 1906. And by the 1930s, it was being applied in research projects in schools in the Philadelphia area in the US to see whether it could control a measles epidemic, and it actually was very effective, as we'll discuss later. So you see here on the screen a number of other milestones in the development of the technology and its adoption. it's now been accepted for tuberculosis control by the U.S. Centers for Disease Control and Prevention for more than 25 years. So it's a very well-established technology. So here in a little more detail is this issue of germicidal action and how that works. So on the left-hand side here, we have an image of a healthy and normal double helix DNA molecule with its base pairs. Adenine and thymine always go together, and cytosine and guanine always go together. And a photon comes in that breaks bonds in some adenine-thymine pairs, the yellow to green. And you can see on the after irradiation image on the right-hand side of that figure, the two yellow thymine bases that have bonded with one another. So that damage makes the replication process work less well. And if there's enough damage, then you will not have replication of the DNA containing microorganism. It's the same process for RNA, only different base pairs may be involved. So the germicidal activity of light has been studied extensively, and while there are some differences across microorganisms, they're pretty similar. So we can use standard inactivation curves or activation spectra, as they're sometimes called, as shown in the figure on the right. And you can see that the maximum effectiveness is around 265 nanometers, and that it decreases rather rapidly in either direction from that point. Actually, if we continued this curve off to lower wavelengths, you would see that it would turn up again, actually down in the far UV region, down there around 220. You have pretty good effectiveness again. And there are some reasons that we might want to use that wavelength range, but it hasn't really been fully developed into widely used products yet. We might be able to talk about that a little bit later on. So mostly we focus on UVC that's as close to that maximum effectiveness point as we can get it. The disinfection curve for ultraviolet is like other disinfection curves, it's exponential. So if S is the fraction of an initial population of microorganisms, the number surviving divided by the number that we started out with, that survival fraction will be, to a first approximation, equal to the exponential of minus KIT, where K is a deactivation rate constant. This is a property of microorganisms that has to be measured, and the units of that can vary, but one way of representing it that's pretty common is in units of centimeters squared per microwatt second, or that would be centimeters squared per microjoule, since a watt second is a joule. And the fluence of UV energy, which really means the amount of energy that's received from all directions. Imagine a sphere around a target, a particle that may contain some viruses. It's that integration over the whole sphere that is the fluence, as opposed to irradiance on a plane, which is what we normally measure with instruments. So that's measured in microwatts per centimeter squared. So the product of K and I has units of inverse time, and T is the time of exposure. So Ki is the time constant of this exponential, and IT is the dose that's delivered. So for any microorganism, there is a dose, I times T, that will achieve a certain survival. And so this is the basic equation for design. If we want to get 90% inactivation on a single pass through a device that uses UV, we know the rate constant for the microorganism, then we can calculate from this equation what I times T must be, what the dose must be. And if we know what exposure time is available, then we can calculate what the fluence needs to be, and that allows us then to design a piece of equipment that will achieve that objective. So there are very large differences in K across different microorganisms, and just a few representative values here. Anthrax has very small value, which means it's very resistant. Influenza is 2 orders of magnitude larger and quite susceptible, as is tuberculosis and as is Streptococcus pneumoniae. I didn't add coronaviruses to this figure, but the coronaviruses that have had their rate constants measured come out around 0.003 something. So they're in the same range as tuberculosis and strep and influenza and measles, which is also not listed here, which means that it's really quite manageable with UV. There are no SARS-CoV-2 rate constant measurements that I'm aware of yet, but the characteristics from one coronavirus to another in terms of their structure, their RNA, would suggest that there probably won't be big differences between the ones that have been measured and the real thing, which we hope soon to have measurements for. So the measurement of this rate constant is a fairly difficult thing, so you'll find in some cases some widely varying measurements under different circumstances, and sometimes they're hard to explain if there isn't enough information about exactly how the test was done. But we do have many, many measurements that we can use in the design process. So now to the UV sources. We'll focus first here on 254 nanometer, which is the vast majority of systems that are being installed today. That is generated predominantly by low pressure mercury vapor lamps. They produce a number of different spectral lines, but the strongest one is at 253.7 nanometers. It's the same technology as we find in fluorescent lamps, with a few significant differences. The big difference is that in a fluorescent lamp, we have a glass tube that's coated with a phosphor. So the 254 nanometer UV that's produced by the plasma in the lamp when we pass a current through the argon and mercury in the lamp to produce a mercury plasma is absorbed on the phosphor on the lamp tube, and it re-radiates as visible light. So if we want to make that a germicidal lamp, we simply have to provide a tube that's transparent to the extent possible to 254 nanometer UV and that has no phosphor on it. 20 to 30% of the input power to a lamp system will typically come out as germicidal radiation, so it's a pretty good conversion rate, input to output. Some of these lamps can last as much as 9,000 hours. Over that time, they'll depreciate substantially by at least 15 to 20%. And some, if they are driven at a high current, will depreciate faster and to a greater extent, but they'll have, at least for a while, a higher output than other lamps. You can see the spectrum of a low pressure lamp on the right compared to the inactivation effectiveness curve. And that 254 line is above 80%, close to 90%. So this is really a very good source. It's a technology that we've had around for a long time. I'll talk about other sources that may replace it, but currently this is the main one. So depreciation behavior of a mercury vapor lamp, this would be familiar to anyone who does much work with fluorescent lamps. There's also, for hot cathode lamps, a shortening of the life based on the switching rate, because every time the lamp starts, we tend to deposit material on the lamp tube that will reduce the output, and the lamp itself is damaged over time. So the depreciation is an important thing to know when doing a design calculation, how much input lamp power do I need? The other thing that's really important is that particularly for lamps that use pure mercury, there is something called a wind chill effect. So the plasma inside the lamp is affected by the temperature of the operating environment, and if the lamp surface becomes too cold or too warm, the output diminishes. So we'd like to operate lamps in an environment such that the surface temperature of the lamp is around 40 degrees C. I think I may have done that conversion wrong to Fahrenheit, but at any rate, 40 degrees C on the lamp surface. That's not the ambient temperature, it's the actual resulting surface temperature of the lamp based on the velocity and air temperature. And we see if we go far in other directions, particularly on the cold side, we can lose a lot of output from these lamps, and that has to be accounted for in lamp selection. There are some lamps that are essentially fluorescent lamps, but not pure mercury vapor, amalgam lamps. And one of the benefits of amalgam lamps is they tend to be more stable across a range of temperatures than our pure mercury vapor lamps, but they still have a wind chill effect, and mercury vapor lamps are the most widely used. So this is a really important application factor, because if you buy a lamp, you may see a rated output that is at room temperature with 0 air velocity, and you may want to apply that lamp downstream of a cooling coil in an air handling unit where the wind chill effect is going to reduce its capacity quite substantially. Now, this is something we studied in a research project a few years ago in my group. We put lamps in a little wind tunnel where we could control the temperature and the airspeed, and we used an infrared camera to experimentally determine the cold spot temperature on the lamp tube surface, and we put a research grade radiometer underneath the lamp in a consistent location and measure the relative output under different operating conditions so that we could develop wind chill maps of lamps. You see on the left in this figure a center of tube cold spot temperature measurement for a lamp in cross flow. So air is coming from left to right there, and on the leading edge of this cylinder in cross flow is where we expect to find the lowest temperature. The other figure shows the hot spot by the cathode on the lamp, where power is being put in. So we use that data to show how you could make maps that show the relative output. Here's a figure that shows the relative performance, percent of maximum output for a particular lamp in cross flow as a function of air temperature and air velocity. And you can see that there are operating conditions around where you might be in an air handler application, say 15, 17 C and maybe 2.5 meters per second, where we're at only 50 to 60% of the output that the lamp can produce under ideal conditions when it's at more of a room temperature condition. So something that always comes up in discussions of UVGI, ultraviolet germicidal irradiation, is the potential for germicidal lamps, the mercury lamps in particular, to produce ozone. The spectrum of a mercury vapor lamp includes a small amount of power output at 185 nanometers, and that is in the range that produces ozone. This figure illustrates how that is easily handled in lamp design. There's some lamp materials like synthetic fused quartz that will transmit 90% of that 185 nanometer UV, and they are going to produce ozone. But if we use a titanium doped fused quartz, which would be the red curve that's off to the right in this figure, you can see that its transmittance at 185 nanometers is essentially 0. So if you simply select the right lamp, which a manufacturer of UVGI equipment should be providing with their equipment, or which you can ask for from the manufacturer, there should be no problem. And in fact, in the United States, UV and other devices that potentially produce ozone are being certified to the UL 876 and 2998 standards. So there's now a test you can do that will demonstrate that the ozone concentration resulting from operation of an air cleaner will be under 0.005 parts per million. And if a manufacturer has certified to that standard, then that product is not presenting an ozone risk. So that's the current technology. We are standardized on mercury vapor lamps, but as in every other aspect of lighting technology, we fully expect that LEDs eventually will displace the mercury vapor lamp because they have, when fully developed, a lot of good characteristics. Long life, they can be configured very flexibly because they're small and can be made into all sorts of shapes. The wavelengths can be tuned. We're no longer limited to the physical characteristics of mercury plasmas. They can be dimmed. They can be cycled without having an adverse effect on the lamp. They behave better in the range of environmental conditions that we see in places where we need to apply UVGI, and they don't contain any mercury. So for all those reasons, we certainly expect that the technology will develop to the point where we will no longer use mercury vapor lamps. Some of the current barriers are the low output of these devices, which is in the milliwatt range, the cost and the durability, and the lack of standards for dealing with them to specify their performance in products. So this figure shows some available UV LEDs, and you can see that we have LEDs that produce wavelengths that go all the way from around 250 nanometers, so 265, which is right where we would like it to be in terms of UVC germicidal effectiveness, all the way up to 405, which is just across the line into the visible light spectrum. There have been some research investigations that suggest that 405 can be germicidal. That's something that's still a developing concept and technology. There's been a lot of work also on devices that are around 360, 370. You see that line there as well. That is in the UVA range, which has a much lower germicidal effectiveness, but is not irritating to skin and eyes, which is something we'll have to talk about with respect to 265. What I haven't shown here is the far UV range down there around 220. That's a completely different type of lamp. We don't have LEDs there yet. It's something called an excimer lamp that produces a strong line around 222. So you can see on the right the relative effectiveness of some of these different wavelengths. So one of the important benefits of LEDs when we have a good opportunity to use them is that they behave much better under different application conditions. And actually, if we take an LED that performs well at typical room conditions, which we need under some conditions, and we put it in an environment that's colder, its output can actually go up. So where a mercury vapor lamp tends to lose capacity in a colder environment, an LED is actually happier there. So there's a lot to look forward to with the development of that technology, but it's not available in the power levels yet that we need for HVAC applications. It's being used for things like disinfecting stethoscopes and other relatively smaller applications. So now let's look at some of the application issues for germicidal radiation, lamp output variation, and its effects that we've been talking about, humidity, safety, effect on materials, and a few words about combining different types of air treatment. So the output of a typical lamp is measured after 100 hours of burn-in at conditions of sort of a normal room temperature and ambient air velocity, and that may not be representative. Depreciation reduces the output of a lamp, so when we're selecting a system, we want to base the amount of lamp power that we specify on the worst case combinations of temperature and velocity, and also taking into account the end of life depreciation of the lamp. Humidity really doesn't have an effect on the output of lamps themselves. Doesn't affect the heat transfer if we go from 0 to 100% relative humidity, and the optical characteristics of the air between 0 and 100% relative humidity don't change enough that there is a significant difference in extinction and absorption of UV along paths of the length that we would typically find in applications. So from one side of a fairly large room to the other. On the other hand, there is an effect of humidity on the rate constant of some microorganisms. It may be higher or lower as the humidity changes from low to high, and that's something that can be looked up in the literature on rate constants when you're doing an analysis for a design. Material compatibility is an important issue if you're doing retrofits. 254 nanometer UVC will degrade a lot of materials that are found in HVAC systems. So if you're using a relatively high-powered system to do air infection in an in-duct application, as we'll talk about here in a few minutes, you need to pay some attention to the materials that are exposed to UV. So some synthetic filter media that may have organic content can be degraded, although other filter media can be cleaned by UV. Gasketing materials, insulation on wiring, and plastic pipe. So these things need to be either substituted for or shielded from UV in application, or you may have a problem over time. So as you see there, a rule of thumb is shield organic components that are within 4 to 5 feet, or about 1.5 meters of germicidal lamps. ASHRAE did an extensive study on this that's documented in the report for Research Project 1509. ASHRAE members can download that report from the ASHRAE website. This is something that I describe in a fair amount of detail in the 3-hour ASHRAE Learning Institute course that I occasionally do, and that's scheduled for June 11th. In case anyone is interested in that, you can look that up at the ASHRAE website and register for it if you're interested in more detail on some of these things. I mentioned safety before. Both UVB and UVC cause skin and eye irritation. UVB is a component of sunlight that reaches the ground, and it has some ability to penetrate the skin surface, and so it's really quite dangerous if you're overexposed to it, because not only can it cause superficial burns, it also can be carcinogenic. But the radiation that we're using in a germicidal application with mercury vapor lamps only affects the very surface layer of the skin, and while it can cause a burn and it can cause eye irritation, it's not considered to be carcinogenic. Nevertheless, we don't want to overexpose. We can get UVB and UVC exposure from leakage out of illumination lamps. So if you have fluorescent lamps that have been in place for a long time, the phosphor can come off of the tube, particularly at the ends, and you may get leaking. Upper room systems that we'll discuss later are actually used in occupied spaces, and if they're not properly installed, they may result in some exposure to occupants as well. NIOSH in the US, the National Institute of Occupational Safety and Health, has established recommended exposure limits for 253.7 nanometer UVC. I've shown some examples of those limits here. So for 1 minute exposure, the most you can be exposed to is 100 microwatts per centimeter squared. that is a level that you might find in some systems that are used inside of air handling units or ducts. At 8 hours, the safe exposure is 0.2 microwatts per centimeter squared, which is quite low. And that becomes a safety criterion for systems that are used in occupied spaces where there might be some accidental exposure by reflection of occupants in the space. We'll talk more about that when we look at that particular application. So to protect people from the effects of exposure to UVC, which are unpleasant. It's like a sunburn and the eye irritation, photokeratitis, feels like having sand in your eyes, and it lasts about 48 hours after you've been exposed, but we don't want that to happen. We can put safeties in systems so that the maintenance worker who's not properly clothed with protective equipment, or someone who just accidentally opens a door, will not be exposed because the lamps will be switched off. Training of maintenance staff is important as well, and maintenance of equipment so that it's functioning properly is also important. So those are some of the main issues. Another point I'd like to make here before we move on to the different equipment types is that we don't need to rely on any one of these three technologies that we've discussed to do all of our microbial control in air on surfaces. UVGI has some good characteristics, and we can get to a certain point with it. Filters also are effective at moving particles, but if we want to do all of the particle removal with filters, that can be expensive, and likewise lots of ventilation to achieve low levels of airborne concentration can be expensive. But find that if you look at the synergistic effects of all three of these, to have some UVGI to a pretty good level of inactivation, 80–90%, and filters that are removing 60, 70, 80% of particulate matter in the range we're concerned about, and a reasonable amount of ventilation, at least meeting minimum standards, that can be a very effective combination that will handle both smaller microorganisms that are difficult to filter and larger microorganisms that may be difficult to inactivate but are easy to remove because of their size. So now on to the various system types. There are room decontamination systems. Many of them are portable, as shown in the figure on the right. These have come to be called UV robots because the more recent of these are motorized, like a robot vacuum cleaner, and can move around a space. So this is used in an unoccupied space because we don't want to expose anyone to a large dose of 254 nanometer UVC. They can be controlled by remote controls, as you see there on the bottom figure, and they sit there for a while and will inactivate microorganisms on surfaces. So these are used a lot in healthcare applications where we're concerned about HAIs and other pathogens that may be in rooms where infected patients are, or where medical procedures may be performed. And this has been shown to be effective on some of the most important HAI pathogens like methicillin-resistant Staphylococcus aureus and Clostridium difficile. This can also be done with fixed lamps, and that's actually a fairly common application too. So instead of a portable unit, you could have a specific room you wanted to clean. You could install a surface cleaning system on the ceiling of that room. Self-contained devices also exist. Here's an example of one that is placed over the head of a bed, and it would have an air intake on the bottom, and inside of the white box you see there on the wall would be a chamber where air would be irradiated, and then it is reintroduced into the room. So this works like any other portable air cleaner. They can be designed to have high single pass inactivation, but like any air cleaner, one of the critical parameters is how much air they move, and whether we get an appropriate number of air changes for the space in which it's being used. You notice in this particular one, it's placed over the head of a patient's bed, this could perhaps be an infection isolation room to try to capture respiratory aerosol. One of the first, maybe the first application of UVGI was the upper room system. So in upper room systems, fixtures are placed either on the ceiling or on walls above the height of the occupied zones. It's important to have a high enough ceiling to do this so you can create a disinfection zone that is not going to result in exposure to occupants. So the fixture that you see there has standard germicidal lamps in it, but because it's installed in this case in a relatively low ceilinged room, it has a lot of plates on it to ensure that the light coming out of it is focused mainly into a horizontal plane with minimal leakage. Lamps as rated, the typical lamp rating at room temperature and low air velocity gives you a good idea of how these are going to perform. There are other fixtures that can be used in higher ceilinged applications where you don't need all of those louvers, and they are more efficient because they don't take out nearly as much of the UV power that's generated by the lamps as these ones that have to be provided with these vanes to focus the beam. So upper room systems have been used since early in the 20th century, and they are used extensively in healthcare applications. The Centers for Disease Control in the US, as you saw earlier, approved use of UVGI in the 1990s, and it's still in their updated tuberculosis control guidelines that were published in 2005. And in 2009, NIOSH published a document on design of upper room systems for tuberculosis control applications, which can be downloaded from their website. And it's a very good guide in terms of explaining how that technology works and providing guidelines on how to apply it. Here you see someone in a patient room, and there's one germicidal fixture on the wall. And you can see that from the little bit of visible light reflecting off the ceiling that this one is not like the other one we saw. The lamp is really open, and they're using the high ceiling in this case to distribute the radiation without having to put something in front of the lamps to prevent exposure of that patient. In-duct systems are another commonly used application. So we put lamps in moving airstreams, either actually in an air distribution supply or return duct, or more commonly in an air handling unit. We call all of that in-duct generically. The reasons for putting the lamps in the air handling unit instead of in a duct, if that can be done, are first of all that we often have higher velocities in ducts than we have in air handling units, so that affects the potential exposure time. And also there's microbial growth on the surfaces of wetted cooling coils that can be controlled by UV. So if we put an air disinfection system in an air handling unit, it can help not only disinfect the air, but it can keep the cooling coil surfaces free of biofouling and perhaps also protect filters. The sizing of these systems really is very dependent on the geometry in which they're installed, how much line of sight do I have, and how fast is the air moving. Here's an example of a commercial in-duct system. This is a few years old. The installations are actually easier than you see here. You see that the manufacturer has provided a channel frame that has lamps attached to it, and those would connect to the ballast, and it's placed a short distance off of the downstream side of the cooling coil here so that it throws light onto the coil surface to disinfect it, and also can dose the air as it moves through. The more recent technologies for installing these, in some cases, actually use magnets, so you don't have to drill any holes in the air handling unit to do a retrofit to install a set of lamps that have been sized and fabricated by the manufacturer. So hook up the power and it's ready to go. This can also be done on filter banks that have a fouling problem. So here's a photo of UV installed to irradiate filter surfaces to keep them clean. This coiled and condensate pan treatment is something that the General Services Administration, the agency of the US government that manages a lot of its facilities, has put into its standards. P100 is the mechanical system standard, and for its highest level of IAQ performance, it requires putting in UV to irradiate cooling coils and pans. It doesn't require air disinfection at this point. The amount of UV that's necessary to disinfect a coil or a filter surface is very small compared to a air disinfection system, because you have an infinite amount of time to irradiate it. So different criteria have been applied. You measure the amount of UV that comes through the coil as one design parameter, or you can measure the irradiance on the face of the coil. Typically 200 microwatts per square centimeter is around where these systems are designed, but some use more and some say that less, even as little as 50 microwatts per square centimeter, is effective. So those are the main technology options. Let's briefly look at effectiveness. I mentioned earlier the 1937 installations in schools. That was written up in a publication in 1942 by Wells and Wilder from the Harvard School of Public Health. This was an upper room application, and they were tracking various infections in classrooms, both controls and classrooms that had upper room fixtures in them. And in particular, they looked at measles outbreaks. So here's a picture from that paper that shows in the center over the students a germicidal upper room fixture. You don't see them like that anymore, but that was what they were using. And on the right, you see two plots that show over a period of time the number of new infections of measles in irradiated classrooms at the top, which was never more than 5% per week, and the infections in unirradiated control classrooms, which were over 20% during the same period of time. So there was a very significant reduction in the incidence of infections during that particular epidemic, and this was done in several schools over a period of years. There was also a paper published in The Lancet several years ago about a double-blind study that was done in 2 office buildings where UV was installed in air handling units, and it was operated on and off in a double-blind manner. So neither the occupants of the building nor the researchers knew when the UV was on or off. And they did some measurements in the building of microbial levels in the air and on surfaces, and they also surveyed the occupants for sick building syndrome symptoms. And the findings for that were significant. 99% reduction of microbial endotoxin concentrations on surfaces in the air handling units, no adverse effects reported, and a statistically significant reduction of symptoms. So this is a study that had a lot of influence on making us confident that these applications were actually beneficial, even in a general indoor air quality sense, not just for purposes like mitigating a pandemic, which is our concern today. The systems for cleaning surfaces have been studied extensively. You find a lot of articles about that in journals like the American Journal of Infection Control. And I'll just say that there have been many studies that show that, first of all, healthcare associated pathogens are treated effectively by UV, and that in many cases, these studies have shown that UV has been more effective than conventional surface cleaning, although that should be done too. But as an adjunct to conventional cleaning techniques, it's been very effective. Now here's the results of a study where a number of different pathogens were measured, and these were rooms that were cleaned for turnover. And you see before manual cleaning and after manual cleaning, there isn't much change. In some cases, there's no change in the number of rooms that were found to have these pathogens in them. But over on the right-hand side, we have the results for UV disinfection after manual cleaning, and what we see there are very significant reductions in the number of contaminated rooms. So in the one case where we went from 21 to 17 with manual cleaning, we now are down to 2 out of 61 after UV. So as I say, there's a large number of studies that show effectiveness. Here's another one on clinical trials that showed 10 to 30% reduction in infections when UV was used to disinfect rooms. For coil treatment systems, this is another thing that we did some research on. I actually worked on a project that ASHRAE partially funded in collaboration with Chandigarh from National University of Singapore. And here are some of the results from an air handling unit in a building there. You can see in the upper left that from before UV, the red data, to after UV, the blue data, there was a significant reduction in the pressure drop across the coil. That was something like 15%. The heat transfer coefficient was found to increase, and that resulted not only in a lower airside pressure drop and less fan power use, but also in less chilled water flow rate through the coil. That reduced by a certain amount. And we did simulation that showed effects on fan energy, pump energy, and even to a small extent, chiller energy. And that's a paper in Building Environment that you can read if you're interested. So briefly about the economics, in US dollar terms, we're talking about something that should be less than $10 a square foot. I did this for upper room. I did this estimate a few years ago and came up with a first cost installed for a system of about $2.50 per square foot. I think you might double that today, but still should be under $10 a square foot based on what I've found from contacting manufacturers recently. And the operating cost is pretty modest as well. So 13 cents per square foot per year for a continuous operation at a typical average electricity cost. That compares to about $2 a square foot per year for energy cost for a typical building. So it's an increase, but not a huge one. These are the relatively expensive and expensive to operate systems, but they have very high effectiveness. An upper room system could have the effect of as much as 10 to 100 air changes of ventilation, as shown in some of the studies that have been done. For in-duct systems, if we look at how much lamp power is required for those systems and the cost of lamps and the amount of air that's being distributed and the typical amount of air that it takes to condition a building with something like a variable air volume system, with all of those assumptions, I estimated a first cost of about 10 cents per square foot for a typical all air system. And that's again a very back of envelope kind of estimate, but less than $1 per square foot. So that's quite a bit less expensive than upper room. And the operating costs are likewise much smaller, the energy use. But the difference between upper room and in-duct is that while I might be able to get the equivalent of 50 air changes with the upper room system, I'm limited for an air handler installation to whatever the air changes are that system produces in supply air. So there's a good cost benefit to the in-duct system, but in some sense, the upper room may be more effective for things like infection control in crowded spaces. So now for a little performance analysis here, and this is just an example of how in-duct systems work to illustrate some of the application issues. So we did a study a while ago, one of my graduate students and I, looking at a system installed in a typical office building, and we modeled the energy use of the system with eQuest, a freely available piece of whole building modeling software, and we modeled the IAQ control with custom MATLAB code, and did an economic analysis as well as a performance analysis, first cost, labor and equipment, and energy cost, comparing filters and in-duct UVGI. So the building was placed in New York City for the climate impact, and we assumed that we had a VAV system that was conditioning interior spaces, so it was always in cooling mode. That was a kind of a simplifying assumption, just to assume that it was running in cooling mode all year. Because in many parts of the world, it actually would run in cooling mode all year. We used typical for the time assumptions about filtration, so we assumed that there was a MERV6 pre-filter, which is what ASHRAE standard 62.1 would have required, and all of the other operating parameters you see there are pretty typical of these types of systems. So we're circulating air through some occupied spaces, which were not modeled in much detail, and the air in the base case goes through our pre-filter MERV6, and we looked at 3 different options. One is that we have UVGI upstream of the cooling coil, where the environment tends to be a little warmer, downstream of the cooling coil where it's colder, and we also looked at a filter that had the same impact on a test particle size as the UV for a microorganism that we assumed to be the threat that we were controlling. So again, those 3 system options here. Base HVAC with downstream UV, base HVAC with upstream UV, and base HVAC with a MERV12 filter added. The reason we did MERV12 was that was closest to giving us the same additional removal of pathogenic particles as we were getting from our UV design. So this figure shows the some of the design aspects of the UV system. We assumed 85% single pass inactivation, and we used Staph aureus just for convenience, and you can see its K value there, 0.0035. Incidentally, that's about the same as a coronavirus, and we assumed that was riding on 1 micrometer particles. We didn't do a distribution of particle sizes. And if we look at the efficiency of removal of those particles by MERV 6, 12, and 13 filters, it's 15, 82, and 90% for a typical filter. So that's why we chose the MERV 12. It was about at the same level as our system. And we used a typical lamp that would go into this type of system, one that had been modeled in our study. I showed you the pictures earlier of our lamp test. This was a lamp that we had studied. And so the box on this figure at the right is superimposed on that lamp's characteristics, and it shows the operating ranges. If we go upstream of the coil, we have a range of conditions that goes from pretty cold to pretty warm, while if we're downstream and in cooling mode all the time, we have a much more restricted range of temperature, and it stays in the cold region. You can see also the velocity range over the course of the year for this VAV system. So when we looked at all of the possible combinations from a year of simulation for temperature and air velocity, it turned out that we had different selection points for the lamp. So upstream of the coil, we had that condition at about 10 degrees C and 1.5 meters per second. And you can see there that the effectiveness of the lamp is at close to 35% of what it would be under the optimal condition. For the supply air condition, it was higher air velocity at the same temperature, and there the output was only about 27, 28%. So it takes more power from the lamps in the downstream configuration because of that to produce the same output as the lamps upstream. And also because the selection criterion is at a higher velocity, that's going to reduce the exposure time at the design condition for the downstream installation. So this shows the results of that in terms of the dose. We wound up to get the same impact needing 364 watts of input power upstream of the coil and 718 downstream because of the combination of exposure time and lamp output. So we included initial costs for installation and relamping costs and energy cost in our economic analysis, and sizing affected all of those things. So I won't go through all the details here because of time, but we used typical values we got from manufacturers for UV equipment and values from the literature for the pressure drop through MERV 12 filters. That's a number that could be quite different depending on the style of filter you use, but we used a fairly conservative one in terms of the pressure drop, 250 pascals additional pressure drop compared to the MERV 6 filter. And we did a life cycle cost analysis on that. We also did a health benefit estimate using the Wells-Riley equation. So I mentioned before in a couple of places, you can take any air cleaner and convert its performance level into an equivalent ventilation rate. The Wells-Riley equation relates the amount of infectious material being produced by infected individuals and the time of exposure of susceptible individuals and the ventilation rate to determine a probability of infection. So what we were doing was looking at the relative risk of infection under a base case and using UVGI. I won't go through the details of this. Those are in the paper we published. And so we had a base absentee rate that we used, and by calculating relative risk of infection and assuming that infected people would stay home from work and knowing what an average person would make in an office building, we could calculate the value of the reduced infection risk that was produced by having UV in the system, or the filter for that matter. So here are the energy results, and what we found was that there were fairly significant differences in energy use between these three cases, and that the filters required the highest energy use and cost, and UV upstream of the cooling coil resulted in the lowest energy cost. Now I should say that coil disinfection generally works better downstream, so that's why many systems are installed there, even though it's true that the sizing would probably be more favorable upstream. If you go to the bottom, you see the cost per square meter or per square foot in US dollars, and for both of the UV installations, they're pretty small. For the filter, fairly significant. And in life cycle cost terms, we get the same thing. Now, without the air quality benefit, we have modest costs for UV and fairly significant costs for filters. If we do include the effect of the UV on predicted effect on sick leave, what we find is that the risk of infection predicted by the Wells-Riley model was reduced by about 50%. So we could reduce our anticipated sick leave cost by that amount. And so that produced a very large benefit. This is always what happens when we calculate the benefits of air quality interventions. The benefit in terms of health was $700 or more per person, or $40 per square meter, so quite large. Remember, we're talking about, in terms of annualized costs, less than $1 per square meter for the UVGI. So that's a pretty good cost benefit. So that's one example of how this technology works. We've published a whole report on the coil disinfection systems, and the economics there can be quite good too, especially when you take into account reduced typical chemical and power washing type of maintenance. So to conclude here, this is not a new technology. It's very well understood. It's been around for a long time. There are a lot of different ways to apply it in buildings to make HVAC systems better in terms of controlling microorganisms, and also to control microbial contamination on surfaces. The best applications are going to be in those where we can actually calculate the value. But even if we don't have a good way of calculating the air quality benefit, we still know that these systems are doing good things when we put them into buildings. And finally, that there are a lot of technological developments coming that may broaden our available options and make the systems even more effective and more cost effective. So if you want to do more reading on this, there are a lot of ASHRAE sources for it. UV is mentioned in the position document on infectious aerosols that was just published in April. And there are 2 chapters in the ASHRAE handbook, one in systems and equipment and one in applications, that discuss the technology. There's a good ASHRAE journal article that was published in 2008 that summarizes best practices concisely. A whole book on UV by Kowalski, who was a student of mine. It's a Springer monograph that covers the technology very comprehensively. It's a 400-page book. And you can download the NIOSH guidelines for upper room TB control systems from the URL. So, and there's much more, but these are some good places to start if you're interested in technology. And so with that, I'll thank you for your attention, and I'll take questions if we have time for those.
Thank you, William, sir, for the very interesting and very good presentation on UVGI, air and surface disinfection. We are approximately near to end this webinar. Before the ending of this webinar, we will take us 5 to 10 minutes on question and answers. So I am seeing lots of questions in my question panel. So first question for you, sir, is it possible to increase power of UVC lamp by using any reflection surface?
Yes, we didn't talk about that, but if you have a non-reflective enclosure, then all you will get is the direct output of the lamp. But if you put it in a reflective environment, you will generate a much higher fluence field and a more uniform one. Fortunately, the reflectivity of sheet metal for in-duct applications is pretty good, so you should take advantage of that. Reflectors are used to focus the output of lamps on coils when you have a purely coil treatment system, but that's important. And because of the reflectivity being important, it makes design calculations for air handler applications kind of complicated, but there is software that manufacturers use that will take into account the reflectivity of the enclosure and the geometric factors, and that ensures that you get a reasonable design.
Okay, thank you, sir. For the next question is, how do we deal with the ozone generation which happens in the UVC bandwidths?
All right, so you'll recall I actually showed a slide on that 2 slides. One that showed that a Mercury Vapor lamp produces some 185 nanometer UV, which causes ozone. As that slide showed, if your tube is made out of quartz doped with titanium, it has 0 transmittance at 185 nanometers. So that's how you control ozone, by using a lamp that has the proper tube material. If you have synthetic quartz, it transmits over 80% of the 185, and you're going to have an ozone problem. So it's critically important to ensure that you're getting lamps that have tubes that will not transmit the 185. Now, the other way you can control ozone is when we move to LEDs. If you get an LED that produces just 265 nanometer UVC and produces nothing in the range that produces ozone, that's not going to be a problem either. So this always comes up, and it can be a problem, but the only way it can be a problem is that if you select the wrong equipment.
Okay, So next question is, will the hot surface temperature of the lamp add additional heat to the airstream? Will this need to be considered during system design or energy modeling? If yes, generally what would be the temperature increase to the airstream before and after?
I've forgotten what the actual number is for a typical installation, but it's extremely small. I mean, we're talking about for a fairly high-powered in-duct system, maybe a tenth of a degree centigrade, maybe less than that. It's pretty much negligible, as is the pressure drop that's caused by putting some lamps in the airstream. So it's not even enough to affect your load and energy calculations before they pass the decimal point.
Okay. The next question is, how can we validate performance of UV lamp in real-time situations?
Well, you can validate that your system is producing the output that it was designed to do. So you do a design calculation to achieve a certain output, and you can take a high-quality radiometer and measure that you're getting the irradiance that you should have at a certain point if you put it in an in-duct system, or if you're looking at the disinfection zone in an upper room system. And measurement of radiation is also important with an upper room system, because you want to make sure you're not leaking more than that 0.2 microwatts per square centimeter into the occupied zone. So it's important when you install those systems to go around and take measurements in different places. There have been cases where it's been installed in healthcare facilities where there are a lot of monitors, and there are monitors all over the place these days, and those screens can reflect UV, and there have been cases where the orientation of the screens was such that they were creating a hotspot. So that measurement, certainly one could take a challenge microorganism and do tests that would require sampling and culturing of either viruses or bacteria, but that's not often done. I think you would generally rely on the design calculation, then show that your system is producing the intended output.
Okay. Now the last question is, what is the estimated fluence necessary to irradiate an airstream? It was mentioned 50 to 200 micron watt per centimeter square for surface, jet, coil, and filters. But is there a rule of thumb based on CFM for airstream disinfection?
Actually, the amount that you would need would go back to the design equation that I showed at the beginning of the talk, right? We have this exponential disinfection equation, and you know what your velocity is through your air handling unit, and you know the rate constant of the microorganism that you want to treat. So you can calculate the exposure time, and for the desired level of inactivation, you can then calculate what the average fluence has to be. And in a lot of systems, that turns out to be in an air handling unit on the order of several hundred to several thousand microwatts per square centimeter. So a lot more lamp power than is required for coil disinfection, but not an unreasonable amount that doesn't have a big effect on either the energy consumption of the system or on the temperature of the supplier.
Thank you, sir. Due to the lack of time, we will not answer the rest of the questions. I request everyone, the questions which are not answered by us, you can write your question at our email ID, ashray.chd@gmail.com. We will answer this question on later on stage. So
yeah, thank you.
Now I thank you all your for participation today. I am very thankful to my ASHRAE Chandigarh team. I thank you ASHRAE Falcon chapter team who help us to promote this webinar. I also thank you youth at ASHRAE for supporting us for this prestigious webinar. So I again thank you all for your participation. We are so grateful for your support. Without you, this would not be possible. Keep participating and learning with ASHRAE Chandigarh chapter. Our next webinar is on 23rd May 2020 at 6 p.m. The topic for the next webinar is two-stage indirect or direct evaporative cooling system. The speaker for this webinar will be Professor Dr. Assam E. Khalil. He's a ASHRAE DL. So, recording of this today webinar will be uploaded on our YouTube channel, digital channel ASHRAE Chandigarh. Please subscribe our ASHRAE digital channel for more videos and for latest updates from the ASHRAE. These are our upcoming webinars which are scheduled by ASHRAE Chandigarh. So our next webinar is on 23rd May. Then next we have 26th May, 30 May, 6 June, and 20 June. At the end, I thank you again, all of you, for the participation. Stay safe and stay connected with us. Thank you.